we are going to look at the October-November 2020 paper 4.1. So let's actually begin. So the first question, is going to be about rate of reaction. So nitrogen monoxide, they react with oxygen. So they have given this equation over there. So what we need to do, by using the rate equation, we need to find out the order of the reaction. This is quite easy. Just look at the number that you have over there. This is going to be second order with respect to NO. So I just write second order. And I also know that this is going to be first order with respect to O. I just write down over there. What is the overall order of the reaction? Then 2 plus 1 is going to be 3. As simple as that. But make sure you remember that the number 2 and 1, we don't get it from here. We don't get it from here. This is actually, we get it from the experimental data. And do remember, not all the time the reactants will be included in the reaction rate equation. So not all the time. But later we will look into this, what we call as a rate determining step, the slower step. So there, you need to focus on the stoichiometric equation. I will go through that in a while. For now, if you look at the second question over here, 2 separate experiments are carried out at 30 to determine the rate of forward reaction. So they are asking you to look at the experiment number 1 to calculate the value of rate constant. So using all the data that you have over here and including the equation that you have over there, you just need to replace. So you just need to put rate, use this value, and then you put all this value over there, and you calculate what is K. Once you calculate, without any problem, you will get the answer over here, but change it into 3 significant figures. This is important. Another thing that students always make mistake is to when they calculate about the units. Now, units, we always make mistake, because of the rate. Because the rate is always measured, in form of mole per dm cube per second. So when you find out the K, you divide it with these two. These two is going to be to the power of 2 to the power of 1. That is going to be divided by concentration to the power of 3. So normally what I do, I just put a bracket, put 3 over there. And what I do next is going to be, I just eliminate. This is to the power of 1, cancel. So if I cancel, so this one will become to the power of 2. So the students will always miss out this per second. So when I bring this equation up, it will become mole to the power of 2. So this will become negative 2. So negative 2. And then dm, negative 6 will become dm to the power of 6. And then students will miss out this. So that is the part that why they will miss out that. Why there is a chat over there, why it is to the power of 3? Quite simple. You see here, to the power of 2 to the power of 1. So this is going to be mole per dm cube to the power of 2. Mole per dm cube. So of course, the unit is going to be mole per dm cube to the power of 3. So this is your math. Something to the power of 2. And then you times with something to the power of 1 is going to be, you are going to get, to the power of 3. So please remember that. So in this case, we are talking about so A. So you just follow the math formula. So in this case, you are going to get this as the unit. Please remember. Try to calculate. Shouldn't be any problem. The only mistake, the only problem that students will face is missing out this per second. Now, then they ask you, after you calculate the K, they ask you to calculate the value of NO in experiment 2. Now they gave the hint, you calculate the K. So now what you can do is, you can just write down rate equals to, rather than putting K, you can use 8.39 times 10 to the power of 3, concentration of NO2. NO to the power of 2, and then the concentration of, you follow here, O2 to the power of 1. So now, what you can do is, you are going to calculate for experiment number 2. So you want to calculate the NO. So you just need to put in the value 6.05 times 10 to the power negative 5 equals to 8.39 times 10 to the power 3. NO to the power of 2, then O2 is 0.005, okay. NO you can calculate, okay, which is going to be 6.05 times 10 to the power negative 5 divided by 8.39 times 10 to the power 3 times 0.005, then square root. Okay, I'm very sure you can get this answer. Okay, so you calculate. But I am going to show you another way. Okay, if let's say they didn't ask you to look for the K, can you still get the answer? Yeah, so there is another way. Okay, without looking for the value of K, you can still get the answer. Okay, this one maybe later I'll ask someone to calculate also. Get ready with your calculator. Now I'm going to show you, okay, how do you use the rate equation without calculating the K? Can we find? Of course, this method is not suitable for this question, okay, because they ask you to calculate the value of K. Yeah, but sometimes, okay, they can ask you straight to question number 2. And rather than giving 1 mark, they can ignore. They don't want to give you this mark. They don't want to even ask you the first question to calculate the value of K. They straight away give 3 marks, okay, to calculate this. Okay, how can you do that? Okay, without calculating the K? I will teach you. Yeah. Now you see here. Okay, of course, this method is not suitable for this particular question, but you can still apply. You will get the answer. Okay, I'll show you now. If you look at the rate equation, rate equals to K and then NO to the power of 2 and then O2. Now, if you look over here, the information that I have, okay, the first thing, 0.002 to become 0.005. I need to times what? Sharon, can you calculate for me? Times what? So how to find? 0.005 divided by 0.002 times by
5/2.
Yeah, which is 2.5, correct. Yeah, so 5/2, so which is 2.5. Now, if this one, we know according to here, we know this is going to be first order reaction. Okay, so Owen, from here to here, if that is first order, this one must times how many? If you times 2.5. No need to think actually. Michelle? Evan, can you try? First order reaction with respect to O2. Yes, correct, Evan. Yeah, 2.5 also. Yeah, you need to times 2.5 also. Okay, but now, okay, this one I put it aside. Okay, but I'm very sure this might not be times 2.5. Yeah, let's actually find out. Okay, from this value to get this value, can we actually find out what is, let's say from here to here, this should be times by how many? So in order to calculate that, 6.05 times 10 to the power negative 5 divided by 1.51 times 10 to the power negative 4, 0.4. Good. Now, it means 0.4. Okay. Now, part of it is 2.5. Okay. How do you get what is here? What is X? 2.5 times what to get 0.4? 0.4 divided by 2.5. What is that? 0.16. Okay, thank you, Owen. Okay, thank you, Michelle. Okay, so you see 0.16. Now, if you look closely at 0.16 and we look at this NO, this is second order reaction. Okay, now 2.5 to the power of 1. Let's actually change 0.16 to the second order reaction. Okay, what to the power of 2 gives you 0.16? Giuliano? Square root of 0.16 is what?
0.04?
Yes. Okay, so I will write this 0.04 to the power.
Wait, 0.4. 0.4.
Yes, 0.4. Sorry. Yeah, correct. 0.4. Okay, okay, let me make it 0.4. Okay, then you will get that. Okay, now it means that, from here to here must times how many? Megan? If this is 0.4 to the power of 2, what is this? Times how many? It is second order with respect to NO. Christopher?
You're trying to get the NO from the second one, right?
You see, yeah? 2.5 already solved. Yeah, 2.5 is here. Yeah. So
Yeah.
0.16 we have, and then we know it's 0.4 to the power of 2. Yeah. 0.4 to the power of 2. Now, we know that this is a second order reaction. So what is the value that must come over here to show that when I find something that is second order?
Wait.
Yeah, like for example, yeah, okay. Okay, if you look over here, okay, let's say, how do I know something is second order reaction or not? Let's say, for example, this one to this, okay, when I say times by 2, okay, second order means times by 4. Am I correct? Okay, that is going to be 2 to the power of 2, right? Now, what happens if I times by 3? Then this one is going to be times by 9, which is going to be 3 to the power of 2. Okay, if you can see the link, okay, 2, 2, 3, 3. The only thing that will differentiate them is going to be the 2 over here. The 2 over here will show you is going to be the the second order reaction. So, okay, what am I expecting over here is, if this is 0.4 to the power of 2, then this is also going to be 0.4, but not to the power of 2. If I times by 0.4, then this one must be 0.4 to the power of 2. That is going to explain this is going to be a second order reaction. Can you understand this, Christopher?
Yeah.
Okay, so therefore, okay, in order to get this value, you calculate. If you get 0.003 times 0.4, you will get 0.012, which is the same as this. Okay, therefore, okay, you can still calculate this without calculating the K. Yeah, so for this question, maybe not suitable, but please take note, you can calculate that. Yeah, now the next part, I'll just move on. Okay, define the rate determining step. Okay, the rate determining step is the slowest step. Okay, the slowest step in a multi-step reaction. Yeah. So the what is meant by slower step? Yeah. So this is the answer for the slower step. But what is slower step? I think a lot of students don't understand what is a slower step. Okay, Giuliano said it's 0.0012. So maybe my mistake. Yeah, let me check the marking key. Yeah, so then it should be another 0. Okay, because I didn't calculate. Okay, 0.0012. Correct. Thank you, Giuliano. Yeah, so this one is going to be another 0. Okay, now, so let's actually move on. Okay, the slower step. What is meant by slower step? Now, always remember, okay, when you have an equation, when you write down the rate equation, we do not depend on the stoichiometric value. Yeah, like for example, this 1 and this 2 will not actually determine the rate equation. So this one you need to remember. Nothing to do with this. Okay, nothing to do with that. So you no need to refer to that. Sometimes, okay, the reactor, not all the reactors also will be included. Because why? Because it's dependent on the experimental value. Now, what is actually really happening over here is because, okay, in a multi-step reaction, okay, the rate equation is dependent on the slower step. And not all the reactants are involved in the slower step. Okay, that is where we get the experimental data. And okay, in the slower step, okay, what you need to have, they will have all the reactant in the rate equation. It means slower step must have this, must have this. Okay, if you have rate equation, slower step must have that. Yeah, and then they must follow stoichiometric equation. For example, okay, if you have to the power of 1 to the power of 1, it means that in the slower step, okay, in the stoichiometric equation, you must have, okay, 1 in front of them. I'll give you one example here. I selected this as my slower step, okay, and okay, I say that this one is going to be slower step. Why? Because this exists, this one exists over here, and very important, to the power of 1 to the power of 1, this is 1, this is 1. That is very important. What students do? Students misunderstood that, okay, they will end up, okay, doing this. Okay, they will end up, oh, I just need to suggest, okay, I know that, oh, this is going to be to the power of 2i. 2i, I put 2i over here. Students put 2 over there. That is wrong, okay? You must put 1i minus only, okay? Because you follow the rate equation. This is very important. Now, some students, they confuse, yeah? They say suggest equation for two-step mechanism for this reaction. They confuse what to do, okay? Now, first step, okay, you decide, okay? Normally what I do, I decide, okay, step number 1 is my slower step, okay? But not all the time is going to be the slower step, okay? But easier if you decide the slower step first, okay? And if you select the slower step, you just look over here, you just make sure all the required information are there according to the stoichiometric value. If it is 1, 1, so this is 1 and 1. You put down first. And don't go and put the product straight, 2SO4, 2 minus, and I2 over there. You must, okay, put an intermediate, okay? So you can come up with your own intermediate. Not necessarily it must be correct, okay? Not necessarily you need to memorize. Not necessarily we don't know whether they exist or not. Doesn't matter, yeah, doesn't matter. Different people, like for me, if I give this answer, maybe it's unique for me. Maybe when Frederick give answer or Thompson give answer, it might be unique for them. So they are not going to deduct mark. Okay, please remember that. Okay, but you need to be very careful. Okay, you need to follow certain procedures. Yeah. So let's say my intermediate, I'm going to put, okay, S2O8. S2O8. Let's say I minus. Okay, I put I over there. Now, you cannot simply create and then put 2 minus or 3 minus simply like that. Yeah, what you need to do, you look over here, 2 minus, minus, total charge, 3 minus. So left charge and the right charge must be the same. That's why I put 3 minus. Don't simply create. That is very important. Okay, so left and right must be the same. Now, once I have created the intermediate, I need to eliminate the intermediate. I eliminate the intermediate here by putting it as a reactant. And remember the main equation, I need 2i minus. I have 1i minus, I put another i minus. And what is your product? Your product is this. Now you put the product in. 2SO4, 2 minus, you put over there. I2, you put over there. When you add these two equations together, you are going to get this equation. Just to check, okay, you check the charge. 3 and -1, -4. This was 2 minus only, don't worry, because 2 times 2 minus is -4. Left and right, they are the same. So this is going to be valid. It's accepted, okay? And what is the rate determining step? Step number 1. If you look at your, if you look at the marking key, it might not be the same, okay? But, okay, the examiner will check and then will assign marks accordingly. No need to must follow, no. This is just an example. Yeah, so it can be unique to certain people. Yeah, so you need to create. Okay, you need to come up with a suggested, okay, intermediate. Okay, now I would like to use the same question now. Okay, and I will try to see whether you guys can understand this. Okay, let's let me try to use this space over here. Now, let's say now I am going to change this, and I am going to put this as to the power of 2 over here. Okay, so just now, okay, you see first order, but now first order and second order. Okay, second order with respect to I. Now I want 2-step reaction. Okay, so step number 1, step number 2. Okay, so now, okay, probably I need you guys to help me over here. Wilson, what might be, which one you want to choose as a slower step? Step 1 or step 2? I let you decide.
Just step 1 like you, sir.
Okay, then this is the slower step. Okay, now follow step 1, slower step. Okay, so Josh, what should you write over there in step number 1? You look over here. Okay, so S2O8 2 minus 1 mole plus I minus how many moles? 1 mole or 2 moles even? No. What did I tell you earlier? Okay, when you are looking into, okay, rate determining step, okay, what did I tell you? Look at all the reactants in the rate equation, follow the stoichiometric value. Okay, if this is 1 and 1, therefore your slower step will have 1 and 1. Follow that. Now you are going to have to the power of 2 for the I minus. So what you need to do is, okay, this is to the power of 2. Must have 2 over there. Very, very, very important. Okay, you must have 2 over there. Okay, now don't go and straight give 2SO4, 2 minus, and I2. You won't have anything to write later. Okay, don't do that. Okay, so instead of writing that, okay, you are going to write or come up with the intermediate. Okay, the best way, if you follow my way, okay, just write down together S2O8 I2. Okay, and then you count the charge, -2. 2 times -1, -2, -4. So I just put 4 minus. This is normally what I do. Okay, and then I need to eliminate this intermediate. So S2O8 I2 4 minus is going to give me what? Because I need to get this, the product. So no need to think so much. You just put in. When you add these two, they are going to give you the equation that we want. But you need to check whether, okay, your charges are the same, left and right. So you see -4 here, -2 only. No need to worry. 2 times -2, -4, 0. Yeah, so left and right is the same. So this is going to be the answer. If they ask you identify the slower step, yeah, step number 1. Okay, is that clear, Ewan? Okay, so now I am predicting this type of question to come out in your actual paper. Please remember, that's why I'm showing you this, yeah? And my prediction is I'm thinking of, okay, rather than showing 2-step reaction, rather than just 1 intermediate being formed, maybe they can ask you 3-step reaction, and they give you one of the equation they give you, and they ask you to fill up the remaining 2 equations. It's possible, yeah? So this one, I don't have any examples, but just prepare. If you have 1 intermediate, of course, you can create another 1 more intermediate also, yeah, which can be cancelled. And you can have okay, 3-step reaction also. Yeah, so please take note. Okay, if they ask, okay, it will be a very interesting question, 3 marks or 4 marks. Yeah, but for now, okay, I just highlight for you, okay, so that you can focus more. Okay, if you want more questions like this, yeah, in my YouTube channel, I have created, I think, 1 video, okay, to discuss about 2 questions on this. Yeah, you just need to type rate determining step or multiple step. Okay, rate. I think you type rate determining step. I think you will get, yeah, you will get that video. Okay, and then you can go through that. Okay, now I will just move on. Okay, now they say that a large excess of peroxide disulfate ions is mixed with iodide ions. Immediately after mixing, okay, they have this initial concentration. Under the condition used, the half-life is 48 seconds. The moment you see or hear about the word half-life, half-life is constant whenever they are first-order reaction. Please remember that. So for I minus, you check again. Okay, I minus, this is a first-order reaction. So the half-life is going to be constant. Okay, so now, okay, they ask you to calculate, okay, after 192 seconds. So first, you find out how many half-life is that, 192 seconds. So it's going to be 192 divided by 48. So you will get 4, yeah, if you calculate. Now, if you are good in maths, then it's going to be easier. But if you're not good also, okay, you can still draw and then still find out. Okay, let's say the initial concentration is IO, yeah. So for the first half-life, it will become half of the IO, okay. And then the second half-life, half of the half IO, okay. And then the third half-life, you will get half 1 over, this one maybe 1 over 4 IO. Just count, yeah. Then after that, the fourth is going to be half of 1 over 2 times 4, 8 of this, okay. In total, okay, this is going to be after the first, second, third, and fourth. Okay, we are looking into 1 over 16. Yeah, 1 over 16 of the initial, okay, concentration. So therefore, I use that value and calculate, and I will get this particular value, okay, which I put it as my answer. Okay, in our syllabus, okay, you should know how to use the graph to find out the half-life. Yeah, because do remember in a graph, okay, if you have, okay, we have 2 types of graph, okay, but I'll just focus on the one graph, which is going to be one graph, okay, is going to be if you have a reactant, the concentration, they're decreasing according to time. Okay, reactant according to the time, they're decreasing. There are 2 types of graph. Yeah, one is like this, another one may be like this. We don't know which one belongs to which. And there is another one that can actually go all the way straight line like this. Okay, this straight line is 0 order. Okay, that straight line is 0 order. But the 2 curve is quite difficult to determine. Yeah, how do I find out which one is first order and second order? Okay, the first order, you just count. Yeah, let's say this is 5, and let's say from in the middle is 2.5. I just find out, okay, the half-life. Okay, if this half-life is going to be constant, let's say another half-life 1.25. If I go and find out, you see this, if I touch this graph, then the half-life is decreasing. If I go and touch this line over here, the half-life remains constant. Okay, I'll just use the red pen over here. Half-life remains constant. Okay, so if I have from here, so you see when it touches over here, maybe roughly here, half-life remains constant. So that is going to tell me that this is going to be a first order reaction. Okay, from the graph, you need to find out. Okay, you need to find out. And second thing is, okay, in our syllabus also, okay, there is a formula that you need to memorize. Okay, you can calculate, okay, the half-life. Okay, if you have the half-life, you can find out what is the rate constant. Okay, the formula is 0.693 divided by half-life equals to rate constant. In this particular question, they didn't ask you to use that. Okay, but please take note. Okay, they can ask you about this as well. Yeah. So I will move on, okay, to the next question, number 2. Now, the lattice energy of 3 ionic compounds are given below, and you can see lattice energy are always negative. So what is, when they ask you define lattice energy, okay, always remember why lattice energy is negative, because, okay, it's energy being released. Why? Because you are forming 1 mole of ionic compound, okay, from its gaseous ion. So there is going to be bond formation, okay, under standard condition. So let's say, for example, if I have CaO, how do I write the lattice energy equation for the CaO? Okay, to form 1 mole of CaO, I need to react with Ca2 plus in gas and O2 minus in gas. This is the equation for lattice energy. Okay, please remember that. Okay, students will get confused, okay, with certain things. I will tell you certain things that you need to remember, whether exothermic or endothermic. Yeah, lattice energy, okay, I will also ask you to answer also. Lattice energy is always going to be negative, yeah, because it's going to be forming the bond. Okay, now maybe I'll call Sharon. Can you try this? Hydration. Hydration, is it going to be exothermic or endothermic, or can be both, Sharon?
Can be both.
Cannot. Okay, hydration cannot be both. Hydration is going to be, you are going to have, okay, Na, it is going to be joining with aqueous to give you Na plus aqueous, which is going to be gas. Okay, that is hydration, right? So you see, it is forming the bonds with water molecules. Okay, so this is going to be bond formation. Hydration is always going to be negative. Okay, please remember that. Okay, cannot be both. No. Okay, it must be negative. Hydration must be negative. Now, solution. Now, enthalpy of solution, okay, can be used to say that something is soluble or not. Yeah. Let's say this particular compound is going to be ionic compound is soluble. Giuliano, enthalpy of solution must be positive or negative?
Can be both.
Yeah, can be both, but let's say it's soluble.
Or soluble, then it's negative or small positive.
Very good. Yeah, soluble. If it is soluble, must be negative or small positive. Therefore, it can be both. Okay, can be positive or negative. If you have, okay, positive, then they are insoluble. Please remember that. So this is going to be the important 3. Yeah, let the soul go and hide. Yeah, so that's why I put that first. Okay, but other than that, okay, you need to also remember one important thing where students always make mistake. So Chai, maybe you want to try this. Okay, what is enthalpy of formation? Is this positive, negative, or can be both?
Can be both.
Very good. Yeah, enthalpy of formation can be both. Okay, you know, but most of the students, okay, most of the students, I mean 70%, they will end up giving the answer which is going to be negative, because they just look at formation. Formation is what? Formation of bond, maybe negative only. Don't make that mistake. Okay, enthalpy of formation, whatever the term that is being used, yeah, in order to form something, it always involves bond breaking and bond formation. Okay, so therefore it can be positive, it can be negative. Yeah, so please remember, it depends, okay, on the compound. Okay, so it can be both. But other than these 4, you need to also know, okay, ionization energy, endothermic, they will always go up. Atomization, always endothermic, they will go up. Okay, your first electron affinity, okay, will always go up or down, Frederick? First electron affinity.
No.
Second electron affinity. Okay, do remember your first electron affinity. Okay, what is electron affinity? You are trying to bring the electron. Okay, 1 electron, you are trying to add the 1 electron to every one atom or ion in 1 mole of the in 1 mole of gases atom or ion. Okay, so it means that you're trying to form bond. When you form bond, it means this is going to be negative. Okay, you are going to form bond. But the moment you form bond, okay, it means you are going to get a negative ion. Now, when you bring in electron to a negative ion, there is going to be repulsion. In order to overcome the repulsion, you need energy. Therefore, second electroaffinity onwards, they are going to be positive. Yeah. So that is going to be if they ask you about, okay, second electroaffinity, third electroaffinity, what happened, you need to actually remember that. Yeah. So please remember all this. Okay. I think I went through most of the stuff over there. Now I'll come back to the question over here. Explain why lattice energy, okay, of CaO is more exothermic than lattice energy of LiF. Now, lattice energy basically tells us that, okay, how is the attraction between two ions, okay? Like, for example, you see the gaseous ion. What is the attraction? If you have more attraction, then they are going to be more negative, okay? If you have less attraction, then they are going to be less negative. Yeah. So if you look over here, when they say CaO is more exothermic, so it depends. If you look at the attraction, it must be depending on the charge density. So the charge density, the formula is charge divided by radius. Okay, we use this quite often. Yeah, charge divided by radius, and you do not need to worry about radius, okay, of Li and F if the first thing, the charge itself, is more or different. You follow the charge, because last time I told you charge will have a dominant factor. Why? Because for charge, they times, okay, the product of the charge divided by sum of the radius. So the radius do not really play a big role. The bigger role is being played by the charge. The moment you see the charge is 2 over here compared to charge 1 over here, you do not need to even talk about the radius. You don't need to even check about the radius. Automatically, okay, the one that has bigger charge, okay, the charge is going to be more, okay. Therefore, the charge density is more. You just need to write down stronger attraction, okay, between what? Okay, stronger attraction between this and this ions, okay, compared to Li plus and F minus. Therefore, okay, they are going to be releasing more energy when they form the bond. Yeah, so I hope you understand this. Now, the next is, okay, use the data and estimate. Okay, no need to focus too much on the values. Okay, they just want you to estimate. So they want for magnesium oxide. Okay, if you look at your data booklet, your periodic table, magnesium is on top of calcium. Yeah. So magnesium, if it is on top of calcium, the charge is the same. Yeah. 2 plus. And then magnesium is smaller. Okay. The radius is smaller than calcium. So if the radius is smaller, okay, we know the charge density is charge divided by radius. If the radius is smaller, what happens? Okay. Your charge density is greater. Okay. If your charge density is greater, they can form stronger attraction. Yeah. Stronger attraction, it means they will release more energy than this value. So anything that is more negative than negative 3513 is correct. You can give answer negative 3515 also correct. Yeah. But I will not suggest you to do that. I will suggest you to give 3600. Okay, negative 3600 or negative 3700. Okay, that will be a good answer. So I selected this one. And if you look at barium, barium is actually lower than strontium. Okay, so barium is bigger. Okay, so therefore, if the radius is bigger, okay, so your charge density is lower. Okay, if charge density is lower, less attraction. If you have less attraction, so you are not going to release that much of energy. So the energy must be smaller than this value. So maybe negative 33, maybe 0.9 also, correct? Okay, but I'm not going to suggest you to do that. Okay, I will suggest to give maybe negative 3200. or maybe -3300 is still okay. Okay, so I have actually selected -3200. Yeah, so please take note of that. Okay, but must be negative lattice energy. Yeah, please remember that. Now, if I move on, write an equation for the reaction of between this and this. Yeah, barium oxide is solid. Okay, when you react with water liquid, they are going to give you barium hydroxide, which is going to be aqueous. So it's all balanced. Yeah, no need to worry about that. Now, this is very important. Yeah, and I told you to also remember. Yeah, solubility of hydroxide in your syllabus. We look into solubility of sulfates and solubility of hydroxides. Okay, group 2. Yeah. So when you go down, okay, for hydroxide, okay, solubility increases. Okay, and then when you go down, okay, group 2 SO4 2 minus, solubility decreases. How to remember? Last time I told you. Okay, when you go down, sulfate, barium sulfate is a white precipitate. So of course, it's going to become solid. So you can remember solubility decreases. For hydroxide, it's the other way around. Now, when you answer this kind of question, you need to refer to the formula, which is going to be let your soul go and hide. Yeah. So this one I told you, lattice energy. Okay, hide. Okay, let your soul to go and hide. Yeah. So this is the formula. Okay, but we will not apply them directly. Okay, we will not apply them directly. And then, okay, when you look over here, when you go down the group, okay, of course, the radius is increasing. For both hydration and lattice energy, when the radius is increasing, okay, your charge density is decreasing. Okay, it means that, okay, the value of hydration and lattice both will decrease. So therefore, you see, solubility increases. You mentioned about that. Both lattice and hydration decreases. That is another point. Okay, but one of them will decrease more. Okay, it means the dominant factor. And I told you to memorize this, and this is how I memorize. I don't know how you memorize. Okay, I told you okay, which is going to be SHH. Okay, where I said I will remember sulfate, and then HH is going to tell me that my hydration, okay, will decrease more. Okay, so it means that for sulfate, I will remember hydration decrease more. So now I'm not doing related to sulfate, it's hydroxide. So what will decrease more? Lattice energy will decrease more for hydroxide. This is how I memorize. Yeah. So lattice energy decrease more than hydration. Okay. Therefore, okay, when that happens, when you put all these, if you rearrange this formula, you don't need to show. Yeah. But when I rearrange this formula, okay, I will notice that when this thing is decreasing more, lattice energy decreasing more, what will happen to my solution? Because now I know solubility is increasing. And Giuliano said, okay, if you have more solubility, it means you must have negative solubility, okay, or a small positive, then it's soluble. Okay, so it means that your enthalpy of solution, okay, is going to become more negative. Okay, when that happens, you don't need to even show over here. Okay, therefore they become more soluble. In that case, if you put in all this, you will get the 4 marks. I'll show you where you get the 4 marks. Solubility increases 1 mark. Both of them will decrease another 1 mark. Okay, the 3rd mark is going to be the lattice energy decreases more. And the 4th mark is going to be the enthalpy of solution becomes more negative. Therefore, it's going to be more soluble. Make sure you know how to change this for sulfate. Okay, please remember this. Always come out. Okay, 1 year it will come out in hydroxide. Another year it comes out as sulfate. So if you don't prepare for this, you're just wasting that 4 marks. Yeah, so please make sure, okay, you prepare for this. Yeah. So I will move on, okay, for the C. Now, use the following data and relevant data from the data booklet. So I took some data from the data booklet also for you, okay. Okay, for Christopher, with sulfate, are both lattice and hydration increasing? No, Christopher. Okay, do remember, lattice energy and hydration, they are going to decrease. Both of them will decrease because as for sulfate and hydroxide, as you go down the group, okay, the radius is going to increase. The radius of cation is increasing. So when the radius of cation is increasing, both of them will decrease. Okay, but what will happen for sulfate? The hydration will decrease more compared to lattice. Okay, so the only thing different is the hydration will decrease faster. Yes, correct. Yeah, correct. Okay, so you just play around with these two. Yeah. Now, so I have taken some examples over there from the some information from the data booklet, and they have given us some information over there. And I have spent the time to draw the full Born-Haber cycle. Now, compared to 2021 paper, okay, this is more straightforward. But I like the way that they asked the question in 2021. Okay, they didn't give you straightforward. They combine the equations. Okay, and they expect you to use that. Yeah, but in this case, this is way easier. You need to draw. Yeah, you need to draw one by one, and this is not so difficult, easy. Yeah. So if you look at what you need to do first, okay, first of all, okay, it's going to be lattice energy of MgF2. Yeah, so that is the first thing that I will write down, MgF2. Okay, and if I want to find the lattice energy later, I will put the lattice energy over there. First of all, okay, I need to look at the formation. Okay, formation. You look at this, and how do I know it's negative 1102? Okay, it's given. Okay, formation. So you draw, okay, going down. Okay, and then, okay, I look at the, okay, the information. Let's see the atomization of Mg147 I put. And then, okay, you see here, this is going to be atomization of F2. Okay, but this one not available here. But I look at the data booklet, I get the atomization of that. Okay, to separate this F2 to become 2F is 158. I no need to divide by 2. Yeah, because why? I am going to use the 2. Okay, so slightly different than the previous example that we have done. Yeah, I am going to use 2F, so I no need to divide by 2. And then, okay, what is this one? This one, you look at your data booklet also. Your first ionization energy, 736, yeah, for Mg. This is going to be your second ionization energy to give you Mg2+, okay? And this is going to be your first electron affinity to become F-, but I need to times by 2. Okay, remember the first electron affinity is negative. Why? I'm trying to form the bond, yeah? So we didn't go into the second electron affinity, yeah, but I times by 2 because 2 atoms of F, yeah? And then the last, okay, is going to be these ions joined together to give you this. That's your lattice energy. So this one is quite simple. Clockwise equals to anti-clockwise. All these, okay, are going to be clockwise, 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 clockwise. This is the only thing that is anti-clockwise. So I just put, okay, anti-clockwise, okay. Y plus electron, of course here, okay, when they remove the electron, first ionization energy, of course they will get Mg plus N plus electron, okay. So Mg plus N plus electron. Second ionization energy, they get another electron, electron plus electron, 2 electron, okay. So you put that, okay, and these 2 electrons will be used when you do the electron affinity, okay, then the 2 electrons will be gone, okay. So anyways, if you calculate, you will get this value. Straightforward, okay, but I don't want you to prepare using this method. I want you to look at 2021 paper. Most likely that method, okay, will be asked again during our paper. Yeah, please prepare or check again 2021 paper. Yeah, now define the term electron affinity. Okay, electron affinity, you see, electron affinity, okay, it can be first electron affinity, can be second electron affinity. So you need to be general. So energy change, no need to say energy release or energy absorb. Energy change when 1 electron, okay, 1 electron is added to each atom or ion, okay, in 1 mole of gaseous atom or ion. Okay, this is very important. Okay, do not be specific, be general, okay, but at the same time, okay, rather than saying 1 mole of electron, okay, I think when I see the marking key, they always write down 1 electron is added to each atom or ion in 1 mole of gaseous atom. Okay, so try to use this way of writing the definition for electron affinity. Always they ask you about definition of lattice energy, electron affinity, ionization energy, bond enthalpy, bond energy, all these kind of definition they will always ask. Yeah, just be prepared. Now, the electron affinity of carbon is given -120. Suggest the difference between electron affinity of fluorine and the electron affinity of carbon. If you look at the data booklet, your periodic table, okay, your carbon and fluorine, they are in the same period. Okay, so when you are in the same period, okay, fluorine is more towards to the right, yeah, of the periodic table, group 7. Okay, so group 17, okay, carbon is going to be group 14. Yeah, so we know that, okay, fluorine has more proton compared to carbon. Okay, so more proton means that they have more nuclear charge. Okay, more proton means more nuclear charge, more positive in the nucleus. So if it is more positive, okay, of course, if you want to add electron, okay, you want to bring in -1 charge to a positive, normally it's neutral, okay, but when you look at it, the nuclear charge is going to be more accepting, okay, if you have more proton. So it will be easier to add the electron to F compared to C. Okay, why? Because more proton, more nuclear charge. Okay, so because it's easier, it means more bond attraction, more attraction. So therefore, the electron affinity is going to be more negative. Okay, that is the reason. Okay, so just to check, Michael, is everything clear? Okay.
Yes, sir.
Okay. Michael, I cannot see you. Make sure you adjust your camera, yeah? So anyway, number 3. Okay, let's move on to number 3. Okay, we have only 5 more minutes. Okay, number 3, identify substances liberated at the anode and the cathode during the electrolysis of aqueous sodium sulfate. Now, if you studied in your IGCSE and you memorize everything in IGCSE, maybe it's going to be very easier for you to answer this. Yeah, but remember, I told you whatever you learn in IGCSE, everything. Okay, because now you have data booklet. You can you no need to memorize anything. You can just use them. Okay, but do remember, because of your new syllabus, okay, they are not going to give you all the data. I do not know when they give you this data booklet is not given, whether they are going to give you all the information or not. I'm not sure. Yeah, because I never seen that paper yet. Yeah, but okay, if you use the data booklet, okay, you can find out, okay, which one is going to be given, which one is selected, which ion will be selected. Like for example, if you have aqueous sodium sulfate, okay, the positive ions are sodium ion, and aqueous contains H+, and OH- from the water. Yeah, so there are 2 types of ions, cations are there. Sulfate, you have sulfate and OH-. Okay, last time in IGCSE they would have actually mentioned that if you have sulfate is a big ion. Normally they don't get they are not selected. Okay, so OH will be selected to give you O2. That is IGCSE. Sodium and hydrogen is lower in the reactivity series, and then they say the one that is lower will be selected, the hydrogen will be selected. But this one is in our syllabus, no need to worry about that, because you can use the standard reduction potential. If you use the standard reduction potential, we know that, okay, Na plus electron to give you Na is -2.71. Hydrogen H plus 2 electron to give you H2 is 0.00. Okay, which one will be formed more? Of course, the one that is going to be more positive. Okay, it will go here. 0.00 is more positive than -2.71. That's why this is selected. This is now I'm telling you. Okay, whatever you learn in IGCSE, yeah, you memorize, but now you apply. Yeah, you apply. So H plus is selected. That's why cathode you will have hydrogen gas. Okay, similar to that for sulfate, if you go and look, okay, you are going to use this. Yeah, you are going to use this. So of course, we want to see which one will go this side. Okay, which one will go that side? The one that will go that side is going to be the one that is going to be, the value must be smaller. Okay, so which value is smaller? Okay, this value is smaller, 0.40. This is bigger, so it's supposed to go this side. Okay, so this is going to be selected. Okay, that's why OH minus will be selected, you will get O2, not the SO4 will be selected. Yeah. So this one, what chapter do we learn? Okay, this one is going to be under electrochemistry, Christopher. Yeah. So this one is all under the more positive will go to the right. I think this one is simple only. Yeah. The more positive will go to the right. Standard reduction potential. Okay. And then you apply for electrolysis. Yeah. You apply for electrolysis and you will get this. Okay. Now, under that chapter, of course, we need to learn how to calculate. Yeah, and this is also a very simple question compared to the previous calculations questions that you have done in the past year paper. This is also straightforward. Yeah, so you see 1.5 hours. Okay, this one, find out what is Q. Q equals to IT. Do remember, make sure change into in seconds. Okay, you get this, and then according to the sample, you see molten. Okay, molten means there's no H plus, there's no OH minus. There's only Na plus and Cl minus. So in this case, okay, I have these two equations, okay, the half equations, and you can see 2 Faraday, okay, is going to give you 1 mole of Cl2. 1 Faraday is going to give you 1 mole of Na. They want you to find out what is the volume of chlorine. They want you to find out the mass of sodium, okay. So how to do? Yeah, first, okay, we know if you're talking about Cl2, okay, find out, yeah, 2 Faraday. So use this 1 Faraday is 96500, you times, and then it will give you 24 dm cube, okay. So 1 coulombs will give you this, okay, and we are looking into 24,300. So you calculate and you will get 3.02 dm cube, okay, you write down. And for sodium, okay, I have changed 1 mole of sodium is going to be 23 gram. Okay, so 1 Faraday is 96500. I count for 1 column. Okay, and then after that for this, okay, what is the mass? When I calculate, I will get 5.79 gram. Yeah, this is straightforward, but this is not what I am predicting or what I'm expecting. We have this equation representing standard electropotential, yeah, for the reduction of this compound, and then, okay, in the acid solution that is given. So the E value is 1.92 over there. Okay, so now, okay, they want you to draw a diagram, okay, for the apparatus that we will use to measure the E value. So when you are measuring the E value, the apparatus, yeah, so we need to first, okay, think about the half cell, yeah, for the half cell setup for the hydrogen cell. So you can see the delivery, okay, for the hydrogen gas, and you can see platinum electrode, you label accordingly. The electrolyte is going to be H plus 1 mole per dm cube, and you will have the salt bridge, voltmeter, okay, and then to measure the E value. And then you have, okay, for this one, you see there is going to be ion and ion. Okay, so the moment you see ion, and we can also see the H plus. So ion and ion, yeah, we have to use the electrode as the platinum. So you can see platinum. And then the electrolyte, we use the H plus, okay, we use MnO4 minus and Mn2 plus, all in 1 mole per dm cube. So you are going to have that, okay, and this is going to be the apparatus that we will use to measure the E value. So you draw accordingly. Now, the next question is, okay, use the data booklet to identify a substance that could be used to oxidize Mn2 plus ions to MnO4 minus ion. Okay, so we want, okay, to oxidize this structure. Yeah, so let's actually look at the entire oxidation number first. Okay, so if you look at the oxidation number over here, this is +2. Yeah, the oxidation number of this you can count, which is going to be calculate, which is x plus -8 equals to -1, x equals to -1 plus 8, it's going to be +7. So you can see that they want you to oxidize. Yeah, if they want you to oxidize, it means in this case +2 to go to +7. Okay, so we want this particular equation to go to the left. So if you want this equation to go to the left, okay, what you need to do is you must join with another E cell, which is going to be greater than 1.52. Yeah. So if you get that E cell, okay, the standard reduction potential, which is greater than 1.52, then that equation is going to, that half equation is going to go to the right. Okay. So you go and look at the data booklet, and I have actually looked at the data booklet and found out that, okay, I've selected this. Okay. Maybe you just go through and see which one is suitable. Okay. But I have found out that this is going to be 2.01. Yeah. And I'm selecting this. Yeah. So you see 2.01 is greater or more positive than 1.52. And I know that this is going to go forward and this is going to go backward. Okay, so when it goes backward, okay, so in this case, I already changed it. Yeah, I have, hold on, yeah. I have changed, okay, this equation to the backwards reaction. Okay, let me check. Okay, so you see here, okay, Mn2 plus, okay, 4H2O. So I put it over here. So therefore, okay, this one is going to be 1.52. Now it's going to become negative 1.52. And now I'm going to cancel the electrons. So we know that 2 electron and then 5 electrons. So I need to times by 5 times by 2, everything. Yeah. So when you join all of them together, this is going to be the equation that you will get. Okay. And okay, write the equation. This is the equation, and the E value. Okay, why, under what basis I selected this? Because I want, okay, something that has more, okay, more positive than 1.52 volt over there. Yeah, the E value, so that, okay, it is possible to oxidize, okay, the Mn2 plus to become MnO4 minus. Yeah, this is important. So 2 marks done. Yeah. So if I move forward, number 4, okay, give the mathematical expression for each of the terms. Yeah, for this one, if you want to give the mathematical expression, quite simple. Just, yeah, pH is going to be negative log H plus, and then Kw, yeah, for Kw, okay, don't go and include the water, because water, we know water, liquid, okay, they are going to give you H plus and then OH minus, 1 mole and 1 mole. So when we write the Kw is H plus, okay, and then OH minus, and then we are not going to divide with the H2O because H2O is going to be liquid. So Kw, we just use this. Yeah, so I just use this. Yeah, H plus, concentration of H plus times with the concentration of OH minus. Yeah, now calculate the pH of NaOH. Now, since we have the Kw, okay, we know that, okay, if you have pure water, okay, the Kw is going to be Kw 1 times 10 negative 14. You can check from the data booklet. Yeah, so this one everyone should know. Okay, you can use the Kw, okay, in this manner. Okay, if you have this Kw 1 times 10 negative 14, the H plus I need to find. Okay, but the OH, okay, we assume, okay, we assume the OH from the water itself is too little. We assume all the OH is actually coming from the sodium hydroxide, because sodium hydroxide, when they dissolve, they give you 1 mole of Na plus and 1 mole of OH minus. So if you are using 0.027, so you have 0.027 over there. So you can calculate what is going to be the H plus, the concentration, and you will get this concentration. After that, you can calculate the pH. Okay, you calculate the pH and you will get 12.4. There is another way to do this, okay, which is going to be, you can calculate POH. Okay, pH is negative log H plus. POH is going to be negative log concentration of OH minus, which is going to be negative log, okay, 0.027. Okay, and when you calculate, you will get, okay, that value. Okay, if you calculate, let me quickly calculate for you. Okay, if you calculate that, okay, log 0.027, you will get 1.57. Yeah, POH. And do remember, because of the Kw, yeah, pH, okay, plus POH equals to 14. This one is still related to this, okay, this Kw. So in this case, if I want to find out what is my pH, pH is 14 minus 1.57, which is you're going to still get, okay, 12.4. Yeah, this you need to Yeah, basically you just calculate and you will get this 12.4. Yeah. Now, 3 significant figures. Okay. Now, the Ka value of chloric acid, this is going to be weak acid. The moment you deal with weak acid, okay, you just know in our syllabus we have this formula Ka equals to concentration of H plus to the power of 2, then divided by HA, concentration of HA. HA is going to be your weak acid. Yeah. So you just need to calculate the pH. So you need to find out the concentration of H plus first. Yeah. So I put all these values, H plus to the power of 2, concentration of the weak acid is given. So you just put over there. Find out, okay, Ka we know. Okay, find out what is the concentration of H plus. Once you find out the concentration of H plus, this is the concentration of H plus. Okay, I use the formula for the pH. pH is going to be negative log concentration of H plus, and you will get pH after you calculate, you get 4.71. Okay, quite simple, quite straightforward. Okay, but in order to do this, okay, you need to memorize the formula. Okay, that's why this is very important. You need to memorize. Okay, so if you don't memorize, okay, you are going to be struggling to find out how to do this. Okay, of course, you can do it by deriving. Okay, but since it's going to be 2 hours paper, I don't think so you'll have enough time, yeah, to derive and so on. Okay, let's move forward. Okay, water and octane 1-ol forms 2 layers when mixed. Okay, so ethanamide, okay, is more soluble in water compared to octane 1-ol. Yeah, so it means basically they are soluble in both. Okay, when 1 gram of ethanamide is added, okay, to water, then shaken with 50 cm³ of octane 1-ol. Okay, they found out that, okay, the water layer contains 0.935 gram. Okay, so what I can do is find out, yeah, in water layer you have 0.935 gram. So of course, what happened in the octane 1-ol? So I can find out 1 gram minus 0.935, and I have this gram. Okay, so if I want to find out, yeah, what is going to be partition coefficient, so you need to define. Okay, so I defined it as this: ethanamide in water divided by concentration of ethanamide in octane 1-ol. Okay, when I do that, okay, of course, okay, this is we count from the gram. Okay, you need to change into mole, and then you find it in terms of concentration. Okay, so here I put 0.935 divided by MR, but I don't put the MR value. Yeah, I just put first, okay, and then 50 divided by 1000. Yeah, 50 cm³, change it into dm³, and then you have 0.065, which is going to be in octane 1-ol, divided by MR. Okay, and then divided by 50 divided by 1000, still 50 cm³. So from here, okay, I can cancel. Yeah, so you no need to find out the value. You can cancel this. MR is the same, ethanamide, MR. Yeah, you cancel and you cancel. Okay, in the end, you are going to get this value. Yeah, straight away, mass divided by mass. Yeah, doesn't matter the MR and the volume. Okay, then you will get the KPC, which is going to be 14.4. So as they mentioned that ethanamide is more soluble in water because we use in water, of course, it's going to be greater than 1. Okay, so you can see 14.4. Okay, so that is going to be the answer for this. Okay, and the trick over here, okay, if sometimes people, students will ask, how about if it is, how do we know is ethanamide in octane 1-ol divided by ethanamide in water, or like what I did over here? So in this case, okay, you just straight away look from the question itself. They say ethanamide in water and octane 1-ol. So water comes first divided by octane 1-ol. So you can use it as a way to give you an indication what divided by what. Yeah, so that is important. Now, this one, okay, is going to be slightly tricky. Yeah, do not actually straight away go into this question thinking it's so easy and just do. Yeah, because first you are dealing with different volume. Okay, you cannot simply cancel. Yeah, you are dealing with different volume, and you are taking 0.935 ethanamide. Okay, then shaken with pure octane 1-ol. You know what the student will do most of the time? Okay, they just use the 14.4, the same thing that you found, and then okay, you just put 0.935 and then divide by X. You forget one thing. Okay, because okay, this is the amount, okay, of ethanamide in water. Okay, and certain portion from here will go and dissolve, okay, in octane 1-ol. And let's take that amount, okay, in mass, okay, which is going to be in gram, as X. So I need to put minus X. Okay, it means that, okay, KPC at equilibrium, okay, you see the ethanamide in water at equilibrium is 0.935 minus X, very important, okay, and divided by the volume. Don't simply take the volume because now we cannot simply cancel, yeah. So it's 50 cm cube, change it into dm cube, yeah, 50 divided by 1000, so it's going to be 0.05. Okay, and I am going to use the X, okay, which is going to be the mass in the ethanamide in octane 1-ol divided by 0.1. Why? Because they say it's 100 cm cube. Yeah, so change it into dm cube, 0.1 divided by 1000. Okay, once you do that, okay, you are going to have equals to 14.4. You just need to go and look for the X. Yeah, this one using your maths. Okay, figure out how to calculate. Yeah, you calculate. Okay, once you calculate, you will get the value is going to be 0.114 gram. Okay, where is the mistake that students will always make? This one. Okay, they will ignore this X. Okay, they will use 0.935 only. Yeah, that is wrong. Another mistake is, okay, they forget, okay, must divide by this, must divide by this. Sometimes they go and add, yeah, 150. Do remember, this 100 cm cube of octane 1-ol and 50 cm cube of water, they don't mix. So you don't need to add them. Yeah, but in certain cases, in normal calculation, we add and to find the final concentration. But in this case, they are immiscible liquids. Okay, so you do not need to add. Yeah, they are just going to be 50 cm cube and then 100 cm cube separately. Yeah, so you cannot simply cancel also. Yeah, so please take note. Okay, but do remember this one. I'm taking into the assumption that I am dividing this, okay, with the same MR, okay, and then I cancel, divide by MR, divide by MR, okay, so I cancel the MR, okay. Do remember, if you are wondering about why suddenly I'm just using the mass alone, because the MR you can cancel, okay, you can cancel. Okay, I will get the answer as 0.114. Okay, I'll leave it in 3 significant figures over there. Now, the next question, which is going to be question number 5. This one is going to be a bit confusing, yeah, maybe a bit difficult, okay, because okay, you need to do certain assumptions. Yeah, so you see a solution is made, yeah, by dissolving this, okay, copper sulfate in excess aqueous ammonia. Yeah, this solution, okay, contains copper complex, okay, with the 4 molecules of ammonia. Okay, so we are going to write the expression of stability constant, yeah, K step. Yeah, so what you do, okay, when you go and put in excess aqueous ammonia, aqueous ammonia contains water. Yeah, so if you have copper sulfate 5H2O. Yeah, this is the assumption. Maybe some students, most of you don't know this. Yeah, this one take note. Yeah, when you have this copper sulfate, yeah, with 5H2O, okay, when you put them in excess aqueous solution, yeah, before it reacts with ammonia, before ligand exchange actually take place, yeah, they are going to form, okay, this when they add this H2O, okay, they are going to have 6 ligands of water, okay, will be surrounding the copper. Yeah, so I will remove, okay, I will remove if sulfate. You see the sulfate, okay, will come out, okay, because it's 2 minus, and you can say that this sulfate is going to be like something like what we call as spectator ion. Yeah, spectator ion. So whatever it is, yeah, when you add with excess aqueous ammonia, yeah, this is going to be changed into this. This is very important. Yeah, they are going to change, okay, from here to here. Very important. Now, once you have that, okay, then, okay, they will react, okay, with ammonia. So you can see like what they want the reaction to happen. It will react, okay, where the 4 ammonia molecules, okay, will do the ligand exchange, okay, with the water. They will remove the water. Yeah, you are going to get this, and you are going to get all these are going to be 0 charge. Copper was 2 plus. Yeah, so it will still be 2 plus, and then they remove 6 water, so 6 moles of water, okay, will be there. Okay, so you can actually let's actually also look at the marking key also. Okay, hold on. All right, I will keep the marking key also here. Yeah. So they want us to find out what is going to be the K step. Yeah. The K step, okay, is going to be, we will ignore the water. Yeah. Water is liquid. Yeah. It's constant concentration. So we don't want that. Okay. So I will have, okay, this K molecule. So I have this molecule and then divided by this. Okay. You see this. Okay, if you don't change to this, you will not get this. Please remember that. And then ammonia to the power of 4. Yeah, because I have 4 over there. Okay, so that is what they want in the marking key also. Yeah, please take note of this. Okay, now after you write the stability constant, okay, state the color of the solution. This solution, yeah, copper with ammonia, this is going to be a deep blue solution. Yeah, you can check from your notes. Yeah, it's going to form a deep blue solution. Now, then, yeah, we have this copper. Okay, this deep blue solution is heated gently. Yeah, and they will remove the ammonia. Yeah, you remove the ammonia. Some of the ammonia remains in the solution and some forms ammonia gas. Yeah, the color of the solution changes. Yeah, a precipitate of CuOH2 is forming, and then you are going to collect. Okay, so they say a sample of this, okay, added to concentrated hydrochloric acid, then you have reaction forming a copper complex Y. This is also going to be concentrated hydrochloric acid, means there's going to be a ligand exchange, okay, will happen. So they will form the, I think if you memorize this, it's quite easy to memorize. Okay, you are going to get this ligand, okay, which is yellow color. Yeah, so a sample of this copper hydroxide also, okay, is added to dilute sulfuric acid. Okay, a reaction also takes place and you get another complex which is going to be Z. Okay, so we are going to they also mentioned that, okay, all these 3 complexes are different color. Okay, let's actually look into one by one. Okay, suggest an equation, okay, for this, okay, to form CuOH as the aqueous solution. Okay, so what will happen? Okay, so they mention, yeah, when this one is heated gently, okay, then ammonia is being released. Okay, so when you heat gently, when ammonia is released, what is actually happening? You need to write down first, okay, this one heated gently, you are going to have copper 2+, okay, with ammonia. All the ammonia, or they say some of it stay there. Yeah, you have copper 2+. Okay, now this copper 2+, okay, after that they say, okay, they are going to be you are going to suggest an equation to form CuOH as the aqueous solution is heated. So what happens? Okay, you are going to form CuOH2. Okay, in order to form CuOH2, okay, what you need to have, okay, because here I have ammonia, yeah, of course I need to have something over here that will give me the OH, yeah, so that one will come from water, yeah, so I just include water over here, okay, and I am going to get, okay, like what they mentioned, they are going to give you CuOH2 form. Yeah, so I put CuOH2. Why I have included water? Because I want to form this. Okay, and what will happen in that process? Ammonia is going to be released. I put ammonia going to be released over there. And if I use the OH, you see water, okay, I use HOH, HOH. And I am using 2 OH over here. So this one already used up. So left with what? This 2H plus. So this is going to remain 2H plus. Yeah. So this is the first equation. Okay. When you are going to have this copper with ammonia heated gently. Okay. You remove the ammonia. And then, okay, you have this precipitate, so you have this precipitate and so on. So this one is solid. If you want to write down also the state, you can write down aqueous. This is going to be gas. This is going to be liquid. Yeah, so this one is going to be they mention it's going to be solution. Yeah, so solution is aqueous. Okay, now suggest an equation for the reaction with this with concentrated hydrochloric acid. This one I told you they are going to form this. Okay, so you just need to write, okay, a ligand exchange. Okay, you are going to react with the 4H HCl, and then you see the 4Cl will come in. So CuCl4. Okay, Cu is already 2 plus, and then Cl is -1, so you have 4, so -4, so plus 2 minus 4, you get 2 minus. And then what will happen next? Okay, you have OH, OH, and then 4H plus. So 1H, 1H, okay, 2 moles of water. Okay, so what will happen to the remaining 2H plus? They will stay. Okay, so this is going to be how to write the equation. Okay, now next question. Okay, complete the table with the color and the geometry. So you see the first one, the Y. Yeah, Y we know. Okay, is going to be CuCl4. This one. Yeah, CuCl4 to minus. Okay, so CuCl4 to minus. Okay, the color of the complex is going to be yellow. Yeah, and this is going to be a tetrahedral structure. Yeah, and then the Z. Yeah, you can see the Z. Okay, it's going to be the reaction take place forming a colored copper complex, which is going to be Z. Okay, what actually taking place? Okay, you have the copper hydroxide with H2SO4. Okay, what happens generally is going to be reacting with water first. Yeah, when they react water, okay, the Cu2 plus, okay, they are going to be combined with 6 ligands of water. Yeah, this one is quite common. So if you have, okay, previously you have this one, Y is going to be yellow, okay, different color. Okay, Z must be different color, and this one is going to be, just now they mentioned that they are deep blue solution, so Z must be different color also. Cannot just it is a complex. I cannot say copper sulfate. Yeah, copper plus sulfate, copper sulfate. No, it's not complex. So you need to come up with a complex. The complex that we are going to talk is CuH2O6 and then remain as 2 plus, and this is going to be the pale blue solution, or you can say blue solution. And you can see 6 coordination numbers, so it's going to be octahedral. You can write down this. Yeah, so this is going to be maybe slightly difficult, maybe something that is not always what we do. Yeah, but it's going to be something that you need to also learn. Yeah, now the next part is going to be explain, okay, why the complexes X and Y and Z are colored and why the colors are different. So Y and Z, yeah, they are going to be attached by different ligands. Yeah, so you need to mention the d orbitals, okay, of the complex. They split into 2 non-degenerate d orbitals. 2 non-degenerate d orbitals means they have different energy levels. So they have different energy gap because of different ligand. Okay, and different wavelength or frequency of light, okay, is going to be absorbed when the electron from the lower energy level is promoted, okay, to the higher energy level. So they are going to absorb different energy. So you are going to see a complementary color, yeah, based on the color that is being absorbed. Okay, but do remember, okay, because our new syllabus, okay, depends on what type of complex. In this case, they didn't specify. Okay, if let's say if I look at Y, okay, I know Y is going to be tetrahedral. Okay, okay, but Z is going to be an octahedral. Okay, if you have, okay, like Y, okay, is going to be tetrahedral. This is being added in your new syllabus. Z is going to be octahedral. Please remember the orbital splitting are going to be happening in a different way also. Yeah. So according to your syllabus, octahedral, okay, when we draw, is going to be up and down side over here. Okay, so you can remember up and down 2. Yeah. So what I do is they are 2. Okay, 2D. There are 2D orbitals. Okay, 2D orbitals. Okay, at a higher energy. Okay, and then d orbitals, you have 5D orbitals. Yeah, so you have 3D orbitals at lower energy. Okay, this is important. Newly added in your syllabus. For tetrahedral, okay, you are going to have different. You will have 3D orbitals, okay, 3D orbitals, okay, which is going to be at higher energy. And the 2D orbitals will be at the lower energy. And the 2D orbitals that they are talking about, yeah, so you need to also know what is the orbital. Okay, these are going to be the dz square and d x square, y square. Okay, these are the two d orbitals, okay, that are going to be slightly different. So please actually go through this, okay, because in March paper, okay, paper 42 March 2021, they did ask question on this, okay, so we are expecting this to come out also, yeah, in your paper, okay, in 2022. So let's actually move on further. Okay, question number 6. Okay, when you have, okay, this 1 mole per dm cube of this added into a solution containing Ag plus, a linear complex is being formed. So they already mentioned you are going to form a linear complex. Okay, so if you have that, okay, so you know Ag plus, how it can form linear complex. So it cannot just simply form a linear complex with only one ligand, right? So they are in order to form linear complex, you have to have 180 degrees. So you must actually have 2 coordinate bonding, yeah, with 2 ligands. And you see that they mentioned that S2O3 2 minus, they are a monodentate ligand. So there will be 2, okay, S2O3, okay, 2 minus, okay, S2O3 2 minus. Okay, so define the term monodentate ligand is a species, okay, that can donate 1 lone pair of electron, okay, to form 1 dative bond to the central metal atom or metal ion. This is very important, okay, dative bond, 1 dative bond, okay, and give the formula of P, including the charge. Okay, this one is quite important also. Just now I told you 180 degrees, okay, so you see must have 2 ligands. If not, you are not going to get a linear complex. Okay, so you will have Ag, okay, and S2O3, okay, then you put 2, okay, you see 2. Don't go and put like this, Ag plus, okay, S2O3 2 minus, or this one must times 2, then you have Ag2, S2O3. No, we are not talking about that, yeah. For ligand formation, it doesn't work that way, yeah. So please take note of that, it doesn't work that way, okay. So this one is going to be Ag, okay, S2O3, because we follow the geometry. Yeah, they say that there are 2 dative bonds being formed. Yeah, so once you have that, you need to count the charge. This is going to be +1. Okay, +1, you have -2, -2. What is the overall charge? Okay, so you add all of them. Okay, so the overall charge is going to be +1. Okay, and then -4. Okay, you get -3. So you need to show the charge -3, yeah. So that is going to be the formula of P, yeah. Now the next question is going to be when you have 1 mole per dm cube NaCN, okay, and then you add to solution P, yeah, which is going to be this one, okay, a mixture which includes a second linear complex, yeah, is being formed. So second linear complex, quite simple. So you have Ag plus, okay, you put Cn. Cn is obviously the another ligand, so you must have Cn here, another Cn over there. I think quite simple. Okay, so in this mixture, okay, they found out, okay, that concentration of Q, which is going to be the one that with the Cn, yeah, the one with the Cn is more. Okay, so when something is more, okay, when you talk about ligand exchange, we are talking about stability constant. Okay, it means that the stability constant, if it is going to be more higher, yeah, so they are going to prefer to form with that ligand, yeah. So in this case, okay, they ask you, okay, first write down the equation. So I just write down, yeah, the previous stuff. I add with the 2Cn. How do I know it's 2Cn? Yeah, because it's linear. They already mentioned. Okay, so I just put over there, and I will have this. Okay, what is the charge? So you see Ag plus Cn is -1, so you have 2 negative. So +1 minus 2 is -1. So that's why it's -1. And then 2 molecules of this will be released. So you can also check the total charges, -3 over here, then -2 over here, total charge -5. Okay, so here you see -1, okay, -1, then 2 minus and 2, so -4 you times, and you will get -5. Left and right, the charges must be the same, so they are the same. So this is going to be valid. Yeah, now suggests a reason why the concentration of Q is much more greater than concentration of P. Okay, so Q, okay, which is with the CN, is more stable. Yeah, so they prefer to form this compared to the one that with S2O3. So it means that the ligand, okay, CN ligand is a better ligand, but we don't say that. Yeah, we just say that, okay, the complex, which is the Q complex, is more stable. Yeah, why it is more stable? Because the K step, okay, the stability constant, okay, to form Q is higher than the K step of P. Yeah, so if it is higher, it means the position of the equilibrium is going to be going to the right for forming Q, yeah, in comparison to forming P. Yeah, so you include that will give you 1 mark. Now name the type of reaction in which P forms Q. So it means there is going to be this ligand is going to be exchanged with the CN. So this is going to be a ligand exchange. Okay, but if you look at the marking key also, they also include some other term. Okay, you can use ligand exchange, which I suggest you to use. Okay, but if you want to write down displacement, ligand substitution, yes, go ahead. But do remember, okay, last time also we learned about this. Okay, if let's say it is forming a precipitate, then the name should be precipitation reaction. If it is forming salt and water, then the name should be acid-base reaction. Yeah, but only when you don't have any other thing, like in this case, there's no other thing that you can use. So then only you use the term ligand exchange. Yeah, please take note of that. Okay, the next part is going to be, you have this platinum. Okay, platinum forms a complex ion with the following formula. So you see, this is the coordination number is going to be 4. Yeah, the moment you see coordination number 4, they can exist in form of tetrahedral, they can exist in form of square planar. So two things, yeah, but the moment you see CN, normally CN, okay, they tend to follow square planar, yeah, unless we are talking about CuCl4, okay, then 2 minus, then they will always follow tetrahedral. Okay, if you follow NiCN4, okay, then they are going to be, this is going to follow square planar. Yeah, please take note of this. Yeah, so it depends. Okay, CN is bigger, so they prefer to use the square planar. Okay, so similar with platinum, okay, because there is CN, okay, they are going to form, okay, square planar, not tetrahedral. Just take note of this. So in this complex, okay, the carbon atom, okay, they are going to have the CN, okay, to bond with the platinum. The complex shows stereoisomer. We have 2 types of stereoisomerism, okay, which is going to be the geometrical isomerism, which is going to be cis and trans, and the another one is going to be the optical isomerism. Okay, so in this case, there are only 2 isomers of this complex. Okay, because they have the CN, so I put the CN because I know it's going to be square planar. Okay, so I put the CN over here, CN over here. Okay, and then Cl and Cl. You can see Cl and Cl and CN and CN, they are side by side. So therefore, this is a cis isomerism. Yeah, and another isomer that I can draw is going to be, I put the Cl and Cl over here, Cn and Cn opposite to each other. Yeah, and that is going to be your trans isomer. So when they say describe the geometry, no problem, square planar. Yeah, and the type of stereoisomerism, you can write down geometrical isomerism. Okay, and if you want to be specific, cis and trans isomerism. Okay, but no optical isomerism. Remember that, yeah. In order to have optical isomerism, yeah, there is going to be, maybe you need to make sure that all the 4 groups are different. Okay, but when it comes to transition metal, I think the one that we are going to look at, maybe if you have bidentate ligand, 3 bidentate ligand, and so on, yeah, then we can have the octahedral structure. Then they can have the optical isomer and so on. For this one, no, yeah, only going to be cis and trans. Okay, so I will move forward. Now, question number 7, okay, they say that phenol is a weak acid. Yes, correct. Phenol is a weak acid. Phenol can be made from phenylamine. Okay, give the region and condition for this reaction. So if you have phenylamine, okay, phenylamine, this is going to be benzene, and then you have NH2. Okay, so you are going to make, okay, phenol. So if you want to make phenol, do remember, okay, if you have phenylamine, you need to change it into benzene diazonium salt first. Yeah. So what you need to do, you need to make sure you have NaNO2 and HCl. Okay. And then you put them, you react them, and you are going to get HNO2. And then you are going to get NaCl. Okay, so this is going to be prepared at 5 degrees Celsius, less than 10 degrees Celsius. Okay, because if you use a higher temperature, they are going to decompose to give you N2, yeah, nitrogen gas. We don't want that. Okay, once you do that, okay, you are going to get this benzene diazonium salt. Yeah, so it means the reaction. How do we get this? Okay, so this phenylamine, okay, if I just write in terms of equations, C6H5 and H2, okay, when I react with HNO2 and HCl, I am going to get, okay, this C6H5N2 and then Cl, yeah, and then what should I do, yeah, with this benzene diazonium salt? I need to warm that with water. Okay, when you warm that with water, you are going to get phenol. Okay, this is how you get, okay, phenol. Okay, so give region and condition for this reaction. Okay, you need NaNO2. Okay, you need concentrated HCl. You need 5 degrees Celsius. Okay, so after you do that, you are going to get C6H5, okay, N2 plus Cl minus. So after that, okay, what you need to do, you need to warm, okay, with water. Okay, so when you warm with water, it will change into phenol. Okay, so benzene diazonium, okay, this salt will change into phenol. So please take note of that. Yeah, now phenol reacts with dilute aqueous nitric acid, okay, under room condition. Do remember phenol, the OH group. Yeah, the OH group is going to be very quite interesting, because OH is an electron donating group. So when they donate the electron, okay, they are going to make the electron density of the benzene ring to become higher. So when the electron density is quite high, yeah, the electrophile, they are attracted. Yeah, they are attracted to react, okay, with the benzene ring. So therefore, okay, if you have normal reaction where you need to use catalyst, yeah, you need to heat up and so on, okay, for phenol, you don't need to do that, because, okay, the electron density is going to be more, so it makes the reaction much more readily available. Yeah, readily available. So here they say when you react with aqueous dilute nitric acid, because normally, okay, you need to react with concentrated nitric acid with the catalyst H2SO4, concentrated H2SO4 with 55 degrees Celsius to get nitrobenzene. Yeah, so NO2 into that. But now if you have phenol, okay, you do not need to have all these conditions. Okay, you just need to have dilute aqueous nitric acid, okay, room condition, room temperature, and so on. You will get, okay, and you can see here, okay, they mention C6H5NO3. Okay, what does it mean? Okay, I know that. Okay, I know the first one, it has phenol. Okay, so I know C6H4. Why H4? I know that the NO2 will come to another, it will replace the H. Yeah, so one of the H will go off. Okay, so the NO2 will come in. So when I try to count, yeah, when I just put them together, okay, I have C6H5NO3, which is going to be matching with whatever that I have over here. So what it is going to tell me, yeah, I know that only one NO2 is going in. So no need to worry about two. Yeah, no need to worry about all. Yeah, so only one NO2. But where do I put them? Yeah, do remember, okay, OH is going to be electron donating group. So they are going to activate position 2, 4, 6. Okay, 2, 4, 6 will be activated. Okay, so here you can see position 2. This is going to be position 4. this is position 6, but position 6 in this case is the same as position number 2. Okay, so we are not going to put 6 nitrophenol over there. So when you name them, yeah, so it's going to be 2 nitrophenol, phenol, and nitro, and NO2 is at position number 2. And if you name this, this is going to be 4 nitrophenol. Yeah. Now, next, okay, you have phenol reacts with excess aqueous bromine. Now, normally when you react, okay, with bromine, yeah, you need to have halogen carrier. Okay. So in this case, if you react with phenol, no need halogen carrier. Okay. And if you have excess, all the positions, okay, will be substituted. What kind of position? Okay, because OH is going to be electron donating group, they will substitute at position 2, 4, 6. Yeah, so 2, 4, 6. Okay, the Br will go in. Okay, and you are going to get 2, 4, 6 tribromophenol. Yeah, so that's going to be the name. Yeah, the next part, describe 2 visual observation. This is very popular. Yeah, when you have 2,4,6 tribromophenol, please remember this is a white crystalline solid. Yeah, white solid. Okay, so white precipitate is going to be formed. Okay, and then the second observation is going to be, since you are reacting with Br2, is a brown solution. The brown solution is going to be decolorized. Yeah, because there is reaction. Okay, so that is going to be the 2 visual observation that we will see. Yeah, write an equation for the neutralization, okay, in which phenol behave as an acid. Yeah, phenol C6H5OH. Neutralization, first thing that should come in your mind, sodium hydroxide. Yeah, so sodium hydroxide with the acid, yeah, weak acid, what will it give you? You will get salt, C6H5O minus Na plus, O minus Na plus, left with what? H2O, so salt and water. So you just put salt and water over there, done. Yeah, and then you have water, phenol, and ethanol can all behave as acid. Okay, so we are going to look at it in form of a different order of acidity. So if you look at this phenol, okay, OH, okay, and then if you look at C2H5OH, okay, when they give you, yeah, phenol, okay, C6H5OH, they are going to give you C6H5O minus and H plus. Okay, water will be still later we will compare. Okay, and then we have C2H5OH. Okay, they are going to be, all of them are weak acids, so they will give you C2H5O minus and H plus. Now, when you look at it, yeah, so this one, okay, the O minus, okay, the electron, the lone pair of electrons, okay, that you exist in your phenoxide ion, okay, what it will do, okay, they are going to go and delocalize in the benzene ring. Yeah, so they are going to be delocalized in the benzene ring, making it, yeah, making this charge to become less negative. Yeah, so it is going to stabilize, okay, you can say stabilize, okay, the phenoxide ion. Okay, so this movement, yeah, the delocalization of electron, okay, the delocalization of electron into the benzene ring. Okay, you can write in full. Okay, delocalization of lone pair of electron from the O minus phenoxide ion into the benzene ring. They stabilize the phenoxide ion, okay, making this reaction to be formed more. Yeah, so it's going to be forming more because it's more stable. In that process, you are going to get more H plus. Okay, but it is going to be different when you look at the ethanol, because they are going to form ethoxide ion. So this ethoxide ion, what is the difference? They have this R group. This is the R group. R group is going to be the alkyl group. Yeah, so this alkyl group is going to be electron donating group. Yeah, so you just need to say the alkyl group is electron donating. Yeah, so they are going to be acting as a positive. They will give you the positive inductive effect. So what is positive inductive effect? Yeah, they are going to push the electron, yeah, towards the oxygen over here. And what they will do, okay, because they are pushing the electron, okay, this is going to make this electron over here, the charge, to become more negative. So when it's more negative, negative and positive, they like to form reaction. So they are going to form more. They will react and form C2H5OH. The position of the equilibrium will be shifted to the left, yeah, because of the positive inductive effect. Because of that, okay, they are going to be less H+, so making it less acidic, yeah. So the most acidic is this, less acidic is this, the one in the middle is going to be water. So you need to explain, okay. So in 3 marks, okay, where the explanation will go, okay, you need to actually mention, yeah, you see, the lone pair of oxygen is delocalized into the benzene ring. Okay, done. Okay, this one will give you 1 mark, this one will give you 1 mark. For ethanol, positive inductive effect of the alkyl, yeah, so, or the ethyl group, so you mention about that. And then you say about stability of the phenoxide ion, yeah, so this is going to be more stable, so it will weaken the bond. If you want to say the bond between O and H is weakened, so more H+ is going to be given, so you can say also that, okay, bond weakening, yeah. And then you say the easier to donate the H+. So that is already the more than 3 points, okay, that is required for you to get the 3 marks over here. Yeah, so let's actually move on. Okay, so question number 8. Yeah, so we have total questions 9. So let's actually move on. Okay, so benzene, okay, C6H6 can be obtained from crude oil. Yeah, benzene reacts with Br2 in the presence of Br3. So this one is a halogen carrier. So forming bromobenzene as one product. Give the name of the formula of the other product that is going to be formed. So of course, okay, if you have benzene and you have the H is going to be substituted. So of course you have Br, so the H from here and another Br over there, they are going to join together. Okay, then they are going to give you HBr. So the name is going to be, give the name of formula. So I gave the formula HBr. So if you want to give name, then hydrogen bromide. Yeah, hydrogen bromide. Now, in the presence of, okay, catalyst, bromine can be considered, okay, to be electrophile. So they already say Br+ is the electrophile. Complete the mechanism. So when you complete the mechanism, do check first, okay, the bond is being formed at this carbon. Yeah, so you just draw from here to here, okay, the movement of the electron, and they are going to have this and this. Okay, show the H+ because later you need to when you draw, okay, this one is not complete, you put the plus over there. So the electron will come from here, okay, curly arrow must be shown, okay. The 2 electrons will go in and they are going to break the bond between the hydrogen, H+ will come out, okay, and then you are going to get this Br over there, okay, and then the circle, okay, the ring will become complete again, yeah. Now, name this mechanism, quite simple, okay, this is electrophile, this is electrophile, this is substitution, okay, all benzene reactions, yeah, they are going to be electrophilic substitution reaction, okay. We do have some other reaction, hydrogenation and so on, okay, oxidation and so on, but this one, whenever we are dealing with substitution into the ring, yeah, like for example, bromination, yeah, nitration, okay, Friedel-Crafts, alkylation, acylation, all these are going to be electrophilic substitution. Yep. Now, benzene can be used as a starting material in the synthesis of this compound. Okay, you see, step number 1, suddenly you have C2CH3. So of course, you must actually have the halogenal alkane, yeah, C2, CH2, CH3, Cl, yeah, sorry, CH3, okay, CH2, Cl, okay, so same, okay, but I'll use this. And then because we are dealing with the Friedel-Crafts alkylation, yeah, so it means you need to have halogen carrier, okay, because you are substituting into the ring. Okay, halogen carrier is required. And after that, doesn't matter what kind of alkyl groups that you have, yeah, when you use KMnO4 alkaline, then after that you go and heat and then you put the acidify later, okay, you are going to get, okay, benzoic acid, yeah, so not necessarily 2 carbon and then must have 2 carbon over here, no, yeah, as long you have alkyl compounds over there, yeah, they will give you a benzoic acid. And you see from benzoic acid, from carboxylic acid suddenly become alcohol. There's only one way that you can do that. Yeah, carboxylic acid you reduce. Okay, so in order to reduce carboxylic acid back into its primary alcohol, you need to use LiAlH4 in dry ether. Yeah, so that is important. And here the last part, you can see that, okay, the benzene ring, then suddenly no benzene ring. It means that it's like some sort of a 3 double bonds has been substituted or do addition reaction. Yeah, so this is going to be addition, electrophilic addition reaction. So this one, okay, you are going to have, okay, the reaction must happen with H2. Yeah, the region is H2, and then you are going to use the catalyst, which is going to be platinum. Okay, so when they say suggest a suitable region, yeah, first you suggest CH3, CH2, Cl for step number 1, and then catalyst AlCl3. Yeah, depending on what you use. If you use CH3, okay, CH2Br, then make sure you use the AlBr3. Okay, you can use, okay, last time, okay, they use FeCl3, yeah, but they have removed it, so let's actually stick to this. Yeah, so you can use either AlCl3 or AlBr3. Now draw the structure of A. Okay, A is going to be benzoic acid, so you just draw. Okay, if they ask you, if they given you everything in skeletal form, it's okay, you can draw, but in this case it's not skeletal form, so you can just use represent them like this. Yeah, so it's correct. Now identify suitable region for step number 3. Yeah, so I already put, okay, LiAlH4 in dry ether, done. Okay, so you just put in dry ether. They want region only, no need condition, but I just write also. And then platinum catalyst H2. Yeah, the region is going to be hydrogen gas with platinum catalyst. Yeah, so that is the step number 4. Yeah, now the next question, deduce the number of peak, yeah, of carbon-13 NMR. So carbon-13 NMR, you see, okay, this is going to be 1 peak because specific for this carbon. Okay, you can put this, okay, into symmetrical like this. You can fold, yeah, and then, okay, let me erase this first, then I'll just go through with you. So you see, you can put this, okay, symmetry over here. This is 1. This carbon is going to be carbon number 2, second environment. This and this can be folded, so it's going to be the third environment for the carbon. This and this is going to be different, okay, same, yeah, but different than 3. So it's going to be 4th, and this is going to be special, so it's going to be 5th. So there are total 5, yeah, 5 carbon environment. So I just put 5 over there. Number of peaks. Okay, let's move on. Question number 9. Okay, I believe the last question. Yeah. Now the proton NMR spectrum of compound E, yeah, is given in CdCl3. Okay. I think this question is they ask question directly. You know, why CdCl3 is used as a solvent? Yeah, this one we answered last time. Yeah. Why CdCl3 is used instead of CHCl3? Yeah, the reason, yeah, is going to be if you have hydrogen there, okay, there will be a peak. Yeah, there will be a peak. So in this case, if you use deuterium, yeah, deuterium over here, there is minimal peak. Yeah, but in our syllabus we say no peak. Okay, there is no peak if you use, okay, with CdCl3. So you can actually use that. Okay. Explain why tetramethylsilane TMS is added, yeah, to give you a small peak over here. Yeah, this one is going to be as a standard, okay, as a reference, okay, for, okay, measuring the chemical shift. Yeah, so it's a standard. So these two very straightforward questions. Yeah. Now, compound E is hydrolyzed, okay, by hot NaOH. Hot NaOH, okay, we have normally when you say hot NaOH, this is going to be hydrolyzed reaction. So normally we try to break the bond, okay, which is going to be the amide bond. Okay, or we try to break the ester bond over here. So here, okay, I don't see there is nitrogen here, so most likely this is going to be ester bond. Yeah, so O2. Yeah, so ester bond. So I know when they say they one of two organic product, one of it is ethanol. So of course, if it is ethanol, I automatically know the another product is going to be carboxylic acid. Yeah. So automatically name the functional group. Yeah, ester. So this ester, okay, the moment we know that is ester, yeah, it will give you a lot of information. Okay, what are the information that I will get? I know ester bond exists. Yeah, so I just put the ester, and I know that when I break this bond, okay, and I have ethanol. Yeah, they say one of the product is ethanol, so I just have to put C2H5 over there. Then only I get the ethanol. Okay, so I already found half of the compound already. Yeah, so I have 3 carbons here. Okay, I need here they say 9 carbons, so I have 6 carbons. And when I look over here, I see generally 1, 2, 3 peaks, yeah, of the hydrogen environment. So when I look closer, C2H5, CH3, CH3, then O, C, and then double bond O, then must be something else. Okay, and suddenly I know that, okay, this is going to be one hydrogen environment. Okay, same. And then I have this is going to be another hydrogen environment 2. So I must have another one more hydrogen environment, yeah, which is going to be the 5 over here. So if I go and keep on writing the carbon, then there will be more hydrogen environment. So the best thing that you can do is to put the benzene over there, C6H5. Okay, if you put C6H5 over there, okay, what will happen? This, and this, they are all sharing the same hydrogen environment. Okay, so therefore, okay, you have 1 peak, 2 peak, 3 peak, which is going to be possible to have that. Yeah, so this is going to be my, okay, the molecule that I'm looking at. Okay, so let's double check also. If I count this, C6H5, and then I have CO2, and then C2H5. Let's combine all of them together. C8, okay, hydrogen 10, okay, C8, another carbon, sorry, C9, C9, hydrogen 10, okay, oxygen, that's 2, okay. So C9H10O2, is that what they want? Yeah, that is what they want. Yeah, so most likely this is correct. Yeah, so describe the splitting pattern. Okay, they say 1.4. Let's see 1.4. Okay, 1.4. Okay, they have 3. Okay, most likely if you have 3 splitting pattern, okay, it means it's triplet. So it means the neighboring carbon have 3 hydrogen. So which one is the one that is going to be representing this? Okay, so the one that is most likely representing this, okay, sorry, the splitting is triplet. Splitting is triplet. The neighboring carbon atom has 2, yeah, because we talk about N+1, yeah, so 2 hydrogen. So I can see this is 3, it means 3 same environment. So you see, most likely they are going to represent for this hydrogen. Okay, and the neighboring have 2, which is going to explain the triplet. Okay, so that is going to be the answer, triplet. Okay, why there is splitting pattern? 2 hydrogen on the neighboring carbon atom. Okay, so that is going to be the reason. And then we are going to look at splitting pattern of 4.3. Yeah, so 4.3 is this one. Okay, so you can see that splitting is going to be quartet. Yeah, quartet. It means the neighboring must have 3. Yeah, 3 plus 1, then only you get 4 quartet. So most likely we are talking about this, yeah, this hydrogen. Okay, and then because they put 2, yeah, and then you see the neighboring carbon has 3 plus 1, yeah, so this is going to be, okay, quartet, okay, 3 hydrogen on the neighboring carbon atom. Yeah. Now, each molecule of compound E contains 5 protons, which give rise to peaks between 7 and 8.5. So here, each of them from here to here, okay, there are 5. So it means basically they're quite close, and then it is going to be 5. Yeah. So identify the functional group. Yeah. So identify the functional group. What functional group? The hydrogen. So they are attached to the aryl compound. Yeah, the benzene. So they are going to be attached to the aryl group. Yeah. So that. yeah, attached to aryl group. And then they ask you give the structural formula of compound E, yeah, because I know for certain now this is compound E and I want the structural formula. So structural formula, okay, you write down as, okay, CH3, okay, and then CH2, and then you have CO2, okay, CO2, and then you have C6H5. I think better to write it down as C6H5, the other way around, yeah. You start from here, then CO2, okay, and then CH2, CH3. Yeah, this is going to be a better way to represent that. So I'll copy this and I put it there, okay. So this is the answer, okay. So if you look at the marking key also, okay, let me show you. C6H5, C6H5, CO2, C2H5. Yeah, so it's okay. Now, and then they say the mass spectrum, okay, includes fragments. Do remember the mass spectrum already changed into your A2, but do remember AS. So it's still 2 marks. They can still ask you, but I'm not predicting this to come out in your exam. I'm predicting the number of carbon, yeah, using the formula, yeah. How to find the number of carbon? That's going to be 100, okay, divided by 1.1 times the abundance of n plus 1 divided by abundance of the n, yeah. So so the one, please actually go through this, okay. So make sure, okay, you can use this formula to find the number of carbon in that compound, yeah. But here, okay, they say the fragment ion 29. So in order to do that, yeah, so you just easiest way is to write down there 12 and 3 is 15, yeah, 12 plus 3. And then if you put this one, 12 plus 2 is 14. So oxygen and oxygen is 32, carbon is 12, C6H5 is going to be 6 times 12, okay, plus 5, which is 72 plus 5, 77. So if you look over here, you can, if you look at 29, so see which combination, this one and this one is 29. So these two, yeah, so C2H5 plus, done. And then make sure you put the plus, yeah. Then 77, you see straight away here, C6H5 plus, done, yeah. So that is going to be that part, okay. And the next part over here, question number 10, okay. They said identify which type of polymerization. So I can see carboxylic acid, alcohol, diol, and dicarboxylic acid. So condensation polymerization, yeah. Acyl chloride, diol chloride, yeah. And then the alcohol over here, the phenol, yeah. 2OH over there. So of course it's condensation polymerization. For this one, yeah, so you can rewrite this. If you rewrite CH3, CH, CF2, yeah, the carbon must have 4 bonds. So definitely must have double bond over there. And then if you look over here, the same, you try to rewrite over there, okay, CH3, CH, CH, and then CH2, CH2. So must have double bond over here. The moment there is a presence of double bond, of course, they are going to go through addition polymerization. And the last one, okay, here, next one is going to be, they give you this, and then they say it can polymerize under suitable conditions. No other monomer is involved, so the same monomer within themselves. Okay, why? Because there is carboxylic acid and NH2. Yeah, so you arrange, okay, carboxylic acid over here, NH2 over here. Later I copied 3 because I want 3. So when you can remove the H and OH, so H and OH, H and OH, and so on. You can actually show, okay, when I write down is nitrogen H, okay, then carbon H, CH3, C double bond O. And just to show, you just bring the H over here, H, CH3, C double bond O. Just to show, bring the H over here, and then C, H, CH3, C double bond O, like this. Okay, they want 3 is done, and then they say clearly identify 1 repeat unit, okay, on your diagram. So repeat unit, yeah, so repeat unit. So the one that is repeating over here, of course, the NH and then up to CO. Yeah, so I can draw here NH and CO. Okay, one repeating unit. Now, they say that it can also exist as two stereoisomers. Okay, so do remember, okay, if it is going to be two stereoisomer, okay, when I look at here also, I know, okay, what they're talking about, okay, because I know this is going to be a chiral center. Okay, carbon, there is hydrogen, there is COOH, there is CH3, there is NH2. Okay, so when you have 4 different groups and you want to actually show the stereoisomer, of course, we are talking about optical isomerism, but you need to be very careful when you show them. Yeah, carbon, you put the hydrogen over here. Okay, this one you put, okay, let's say hydrogen, so I put the CH3 over there. Okay, this one you show, okay, like this. Okay, maybe I show COOH, and then here you can actually show something like this going behind. Okay, that is going to be an H2. So when you draw, okay, the mirror image, okay, you can just, okay, put C, H, this one line, just follow the mirror. Yeah, just go here, then CH3. This one, if the mirror, if it is coming here, okay, to here, so of course this one have to come over here. And then you just put COOH, and then here, okay, NH2, you just put NH2. Okay, so this is going to be, okay, the diagram, 3D diagram. Okay, and then the type of isomerism, optical isomerism. Now, for this question, yeah, they say that you put with hardener. Yeah, no longer in your syllabus. I'm just going to ignore this. But okay, this one can quickly do. Yeah, the hardener is diamine. Diamine, they say alkyl chain with 2 amine groups which are not bonded to the same carbon atom. So you have different carbon atom. So NH2. So I just draw over here. Okay, if you want to skip this also can. Yeah, so draw the structural formula, okay, of a compound that will make a suitable hardener. Just need to follow this only. So if I want to draw a structural formula, then it's going to be NH2, okay, CH2, CH2, NH2. Yeah, this is, okay, you don't use this. Okay, structural formula means, okay, it must be like what I've done over here. Okay, with that, okay, we have done, completed. Yeah, so I will stop record.